Why is that interesting? There's like interesting many-body physics because you have competing length scales, length scale of the separation of the atoms and the length scale associated with this interaction. And of course, it's also kind of interesting from a, let's say, technological perspective in that you can think of this array, it's an ordered array, as kind of a register, and the long-range interaction as a way to induce qubit interactions, and so to use it as a type of quantum information. So I want to speak a little bit, motivate a little bit more this aspect of competing length scales. So what do I actually mean by competing length scales? And one very nice example that I think captures this quite well is the example of spin frustration. So first, forget about long-range interactions. Just think about this triangle with 3 spins of antiferromagnetic interactions on the corners. As all of you, I guess, know, this is kind of a frustrated system. If you take 2 of the spins, 2 of the rotations of the spins, you have antiferromagnetic interactions. The third spin doesn't know where to point. You have like degeneracy in the ground state. For this, you don't need long-range interactions, but you can actually translate or transform the system into a linear chain, and you will actually have exactly the same configuration where a third spin doesn't know what to do when 2 spins are fixed if interactions are extending beyond the nearest neighbor. So it's kind of a competition between the nearest neighbor interaction and the next nearest neighbor interaction. This is kind of the theme that I think long-range interactions are, ideally suited to explore, and this is actually experimentally demonstrated in this very simple toy model with optical ions. And in this spirit, there's actually been very many ideas, very many proposals on systems that show very interesting, phases, very interesting effects, just because of this interplay of long-range interactions and competing interaction-induced length scales with a second length scaling system. For example, these tunable quantum spin systems. So these are actually all Rydberg tailored proposals. So there's been ideas to use these Rydberg systems for making systems showing fluctuations in topological order. There have been ideas to use these constraints that are given by a shorter and stronger range interaction to constrain a Hilbert space to get dynamical gauge fields and do autonomous annealing, kind of related things out of Peter Dollich's group of Innsbruck. And if you allow the particles to actually move, there have also been predictions that this motion interplaying with the long-range interaction can give rise to phases like supersolids. And this actually was one of the original motivations for us in Munich to start looking into these Rydberg systems, because we wanted to see if in our experiment we could actually get something super solid. And there's actually some complication with that, and I'm going to tell you in the course of the talk our work towards getting long-range interactions and these motional dynamics of atoms, together, how you can achieve that. Before that, I want to briefly sketch out other systems. So I said I'm going to focus on atoms combined with Rydberg states. I want to briefly show you other systems that you can use to get long-range interactions. These are experimental platforms, let's say selection. One I already mentioned is trapped ions for interactions of infinity range. And there's a lot of work from the ion groups, very beautiful work on quantum simulation of long-range interacting systems. There are atoms that are not sitting in the lattice but trapped in microcaps, which have been combined with Rydberg excitations, which have shown really, really great results recently. So this is very closely related. There's magnetic atoms, obviously, which are also being pursued actively here. I think at Stanford that show magnetic dipolar interactions, and there's been nice results also out of Innsbruck and Stuttgart. And there are dipolar molecules where you use an electric dipole to get these long-range interactions. So there's kind of various platforms. And very broadly, you could say these platforms can be classified as like bottom-up platforms, where you kind of take individual particles, individual atoms, and you kind of put your quantum system together and you introduce the long-range interactions later. And they're kind of top-down approaches where you start with a big experiments. You take a bunch of atoms, you cool them down, and then by their inherent properties, they kind of get these long-range interacting phase, or they have long interactions inherently, and then once they're cold enough, you actually see these. And our experiment is kind of somewhere in the middle because we have a top-down approach, and that we cool the gas of ultracold rubidium down to very cold temperatures, but then we introduce interactions later by coupling to Rydberg space. So what is our experimental platform? It's this quantum gas microscope. So it's, as I said, an experiment set up to produce a degenerate gas of ultracold rubidium-87, a two-dimensional gas of ultracold rubidium-87. And for detection, it's actually special in that it uses a high-resolution objective to image those gases. And it's not only special in its high resolution, it's also special in that we can see individual atoms and the position of the individual atoms. So we have single particle sensitivity, single atom sensitivity. So we can see in this example of thermal cloud, we see, or modern later, we can see individual atoms and their position. And this is a very powerful tool to measure and control ultracold atoms. And many of the experiments I'm going to show you actually start preparing such a 2D gas in this mod insulator state. Mod insulator state is a state where in a lattice, you have exactly one atom per lattice side in one single layer of a lattice. So it's like an array of atoms that you can think of that, that you can image and compare with lattice. And this is a very good state because we exactly know that there's one single atom. So we don't have double occupancies, there are no on-site interaction shifts, which you have. For example, in DC is really a well-defined initial state. So most of the experiments will start from this one insulator. So I told you that there are very, very neat detection techniques that these quantum gas microscopes give you. They also give us very good control techniques. Because starting from such a mod insulator state, we can actually, using the knowledge that there's exactly single atoms per side, we can actually target or design any arbitrary density pattern by using light patterns. So we can use a light pattern that shine onto the atoms and a targeted pattern to cut from this initial mod insulator different final density distributions. So we have a very good control over what starting state we have. So we could, in this case, for example, think about an initial 2D system, but we also can go to this 1D, quasi-1D geometry to get different, to explore different physics. And this is something we use a lot. So this technique enabled by the microscope is very useful for controlling your initial density pattern. And just to give you a brief impression of what all of this looks like in the lab, so this is like experiment. It's a single experiment. We have like the main table where all the data cooling happens, where we prepare this gas. We have the camera, the objective, and everything to look at this vacuum chamber. And then we have another big table clustered with lasers that we need to cool and image and manipulate. So it's a pretty complicated. So that's a little bit of introduction. Here's the outline for the rest of the talk. So I'm going to step back and actually tell you a bit more about Rydberg atoms. What are they? What are their interactions like? What do they do? And why are they interacting the way they do? And then I'm going to tell you how to get from that to many-body systems. So what kind of many-body physics can we explore? Then I'm going to step one step further and show our work on how we can actually get into this regime where we don't only have a frozen gas where the atoms don't move, but where we have motion of the gases. And then some fun topic that we stumbled across more or less accidentally follows. And then maybe if there's time, I'm going to talk a bit about the person's work, which is cavity QD. So let's start with the basics. What are Rydberg atoms? So I told you we have ground state atoms. Ground state atoms typically don't interact over a long range. They have short range interactions. In order to make a long range interaction interacting, we actually want to excite them to very highly excited states. Those are the Rydberg states. Rydberg states are highly excited states close to the ionization threshold. That makes them actually pretty large. So you can imagine taking an electron from an atom, from a rubidium atom, and sending it very far out into an orbit that is very close to the ionization threshold. That means the atom is much, much larger. So here's the size comparison, the ground state atom versus the Rydberg atom. So they're way, way larger. And actually, they're almost as large as the interparticle separation in our lattice. So it's a crazy scale for an atom, basically. The fact that they're highly excited also means that the lifetime is actually longer than the lifetime of a lower lying excited state. And it's in the range of 25 microseconds. And this is long for an atomically excited state, but it's very short compared to any motion in the lattice. And the interaction energies, and this is actually the most notable scale here, is massive. So it's 2.4 gigahertz at 1 micron for the specific state. And that's an energy scale that if you compare it with temperatures or something in a cold gas, it's just orders of magnitude larger. So just to give you an idea, 2.4 gigahertz are about 15 millikelvin, and the temperatures of the gases that we start out with are nanokelvin. So it's a vastly different energy scale. And this is actually the special thing about these Rydberg states. They have very, very different energy scales. And one consequence of this lifetime that is actually very long compared to, as I said, the underlying excited state is that, but it's very short compared to the motion, is that we can consider all the atom states. So even if we didn't have a lattice that would hold the atoms, we could actually neglect any motion because during the short time that the Rydberg states are excited, they don't move. But still, because the interaction is so large and it actually vastly exceeds inverse lifetime, we can see strong effects of that interaction. So we have a hope to get like coherent interactions and see those in these Rydberg states. So what are these interactions? So I put a little note here. These interactions are actually due to a very, very easy or large polarizability of these Rydberg states. Imagine the electron is very far from the nucleus, from the core of the atom, and that means it's actually very easily perturbed. And this perturbation in second order perturbation theory actually leads to van der Waals interactions. You know, you have two neutral atoms that have both a dipole moment, you can actually get van der Waals interactions acting between these atoms. So if you produce two Rydberg atoms, then and you look at the distance dependence of the interaction energy of these two Rydberg atoms, they will actually repel with a strong 1 over r to the 6 characteristic. And as I said, the scales of these interactions are very, very large compared to any other scale in the problem. One other scale that to think of is actually the scale of a laser trying to excite two ground atoms into Rydberg atoms. And the energy scale associated with that would be like the driving strength of that transition. And this interaction is so large that beyond a certain distance, a certain minimal distance, the laser is not strong enough to drive to doubly excited state because the doubly excited state shifts out of resonance. So in consequence, if you just excite a gas of atoms into a Rydberg state, there's actually an excluded volume telling you that if you have created one Rydberg atom, you cannot create a second Rydberg atom in the vicinity. So there's a Rydberg blockade effect that is given by the scale of interaction and the driving strength. And its blockade radius is large compared to the interatomic spacing. And this is actually one first example for these competing length scales. So here the interaction gives rise to a length scale that is somehow competing with the interparticle distance. In this case, it's actually large compared to the interparticle distance, and this gives rise to it. And I'm going to show you one example just in a couple of slides. The first question is, of course, well, how can we probe this in an experiment? Can we probe it? And the answer is yes, we can. So we can prepare a bunch of atoms in the ground state, and then we just like excite it with 2 photons. We need 2 photons to overcome the large energy difference between the ground and the Rydberg state into the Rydberg state. And then after some time, we can actually detect them by just depumping them back to the ground state. And what we see is a bunch of atoms that we know were in the Rydberg state before. And actually, in order to get such a picture, while the atoms are in the Rydberg state, we have to get rid of all of the remaining ground state atoms. We do that with a rapid optical push-out, such that, in this case, it's really a background image of just atoms that were in the Rydberg state. And then, once we have such an image, it's also very easy to actually evaluate like whether there's some kind of blockade. And the way we do that is by looking at a correlation function. So we basically check how likely is it to find another atom close by any single atom, and knowing that they were in the Rydberg state. And what we find is actually a correlation function that has a strong anti-correlation for short distances, which is exactly what you would expect for a blockade. So we can actually see using this microscopic information and the high resolution detection, we can actually see this block directly in our experiment in this correlation function. Good. So now I want to move on and using this interaction that we can see the effect of in this correlation function, and using the detection and the presentation technology that I've just shown you, I want to move on and look a little bit about many of the things that we can do. And I want to specifically talk about spin models with Rydberg interaction. And it turns out that the toolbox I've presented, so this excitation laser and the Rydberg interactions, can actually map to an Ising model, to a spin Ising model. And the way this works is that the optical coupling, so the two-photon laser driving, directly maps onto a transverse field. In this case, we think about the Rydberg state as spin down, or spin up actually, and the ground state as spin down. So we are driving that transition, or driving that transition acts like a transverse field in an Ising model. We can think of an optical detuning as like a chemical potential or a longitudinal field in an Ising spin language. And the Rydberg interaction actually maps onto a spin interaction, like a Ising interaction that is different from the Ising interactions we normally see in the textbook, and that is actually a long-range Ising interaction. So it's not just nearest neighbors that interact, it's also next nearest neighbors and beyond that. So you can write down this Ising model based on a laser-driven Rydberg gas. And then we combine this basically with our initial state. So you think of these 2D clouds of atoms with an atom inside, whose density we can control using the spatial addressing, as having 2 degrees of freedom, which is basically the spin degree of freedom we're going to consider. And the Hamiltonian governing dynamics is this Ising Hamiltonian. And in the following, I'm actually going to show you some experiments we did to test like this Ising model, to try to actually explore this Ising model. And before doing before showing you the result, I actually want to briefly discuss the structure of the phase diagram, let's say, of this Ising model, because there are like 2 interesting phases. There's a disordered phase, first of all, which is like in the conventional Ising model that you know, is a phase where you kind of strongly drive spins, so you don't have a spin order. All the spins just align with the transverse field, with the driving field. And this is the phase where omega is large and delta is kind of small. But then there's another interesting phase, or there's also an interesting phase, which is the ordered phase, which is the phase where interactions actually start to matter. So it's the phase where the interaction current dominates over the driving and the detuning current. And this is this phase actually shows a staircase-like structure, especially if you go to very low driving. Staircase-like structure in the magnetization. So you can think of that like you're trying to excite spins. You can actually not excite all the spins equally. You can only excite those spins where the longitudinal field overcomes interaction inertia. So there's going to be this competition again. And the more longitudinal field you apply, the more excitations you can put into the system, because you can overcome this interaction energy. And this gives rise to this staircase-like structure for small driving strength and increasing detuning in this case. And the goal of our experiment is actually to explore the phase diagram. And in the first experiment, we're actually going to try starting in a state where all the spins point down by following a trajectory to the phase diagram by varying delta and omega to end up in a specific target state. So we want to adiabatically ramp the system from one ground state to another ground state. And here's the way we did that, or we wanted to do that. So here's again the phase diagram I just showed you. What you see here on the left is actually a 2D view of the phase diagram with the path that we're trying to follow indicated, and it's actually a path that starts down here, where we know all the spins, the ground state is the state with all spins pointing down, then increasing the omega, and then like punching back into this low somewhere, this kind of this trajectory. And the way the experiment goes is we follow this trajectory in a time-dependent way, and after certain steps, we just stop the time evolution and we look at the density of Rydberg. And you can actually look at these pictures in this 1D configuration, what you expect in an ideal case. For example, here is to see this like chain of arranged Rydberg states, this crystalline state, if you like. And of course, we want to do this many times and look at the density. And here's actually what we get. So we follow this path in a dynamic way, in an optimized way, actually. And we take these snapshots and accumulate statistics, and here's the density. So we see at this first point, we actually don't see clear structure in the magnetization density. At the second step, you see that, okay, there's something happening. We see a strong increase of density at the edges of the system, but no peak in the center, or at least no strong peak. And only once we like ram all the way into this low, we see like this marked three-peak structure, which is kind of what you expect for this time state. So we basically followed this trajectory, and doing that, we prepared the system close to the ground state at least at 3 different points in the space-time. Then, of course, this was a 1D result. Of course, the question is also, can we do this in 2D? And the answer is it's possible, but it's way harder. And we actually couldn't do it adiabatically, but what we can do is we can compare just hitting the system with a hammer, so doing a quench experiment with this like adiabatic or near adiabatic sweep, and we can actually see that if we hit the system with a hammer, we see more or less a homogeneous distribution of excitations in the system, whereas when we try to stay close to the ground state, we actually see this ring-like structure, which implies that the excitations have enough time to kind of push themselves apart as far as possible to minimize their interaction. But we weren't able to exactly prepare the same state all the time, but sometimes, now and then, we would get these nice snapshots where we would actually get these nice Rydberg crystals. And if we could have done this adiabatically, we would actually have to have been able to really get exactly this configuration, or exactly this configuration in controllability. But this is very hard to do because the gaps are essentially fixed. So it's possible to get to stay near adiabatic in 1D, but it's very hard in 2D. Good. So this was all frozen gas dynamics. This was all spin physics. I told you it could be very interesting, or I think it's very interesting to also explore moving atoms with this Rydberg interaction, with long-range interaction. The next topic actually deals with the transition from one to the other. And why this is a hard transition is shown kind of on this slide. I already mentioned this a couple of times. There are basically 2 different energy scales. If you put atoms in a lattice and you have them interact via Rydberg interactions. There's, on the high energy scale, let's say for our standards, there's these Rydberg interactions, which can like be several gigahertz. There's a Rydberg laser coupling on the megahertz scale, and a Rydberg decay, which is like 1/45 microseconds, so that's on kilohertz scale, which in terms of time scales would be nanosecond, microsecond, millisecond, and millisecond is actually the time scale where you would see motion of atoms in the lattice. So there's kind of a stark contrast between these high energy Rydberg physics experiment, where the atoms don't move, and Hubbard physics, which is a picture that kind of represents Hubbard physics. Hubbard physics where atoms move and timescales are more like moving. The question is, how can we bridge this gap, and can we actually see what we expect to be somewhere between those two extreme cases? Can we see the supersolid? And I can't answer the question of whether we can see a supersolid. I can actually answer that we couldn't see it, we tried, but I can answer how we can try to bridge the gap. And the idea for that is, has been out there for a long time. It's so-called Rydberg dressing. And Rydberg dressing actually is conceptually very simple. You just take your ground state and your Rydberg state, and rather than deciding, actually in the Rydberg state, you only admix the Rydberg state. So you do a detune excitation. And in this case, you can actually just focus on this ground state. You get a new ground state that is basically the old ground state with a little bit of the mixture of the Rydberg state. This little bit of the mixture means that there's some of the Rydberg interaction also for this ground state, but of course, by admixing some of the decaying Rydberg state, you also get some of the lifetime, some of the decoherence that is attached or associated with the Rydberg state. And that's something you don't want because that is right. We don't want it at this point. So conceptually, this is very simple. And the question is, of course, does this work? So, and how does it work? What does this mean? And there's actually a good way to see that this gives, from my point of view, a good way to see that admixing these interactions gives rise to these Rydberg interactions gives rise to interactions between the dressed ground states. And that's looking at kind of the full energy of this off-resonantly coupled system for two atoms, including Rydberg interactions. So that's what I'm going to do. So here's an energy level scheme, let's say, that again plots out the two atom states, energies versus systems. And you see similar picture as before with the 1 over r to the 6 potential, which is due to this weakly dressed Rydberg state, which is still basically Rydberg state. It still has 1 over r to the 6 character, and you have like two basically flat curves, which are the GR states or the GG states, but not like the bare ones, but the dressed ones. And what we are interested in now is like the GG state, which is the lowest one here, or I should say the tilde G state, which is the lowest one here, and we're interested in whether there's some interaction. And the answer is in second order, there's still no interaction effect, so you basically just see, if you look in second order, that this line, this GG line gets shifted down. That's just an AC start shift. But if you go one order higher, you actually see, so you have to blow up the energy scale, you see, oh yes, there's actually distance dependence also for the G tilde state. And this is what an interaction is. So you have a change in the pair state energy when you change your relative separation. So you can actually see in this case that admixing comes to Rydberg interaction to the ground state gives rise to an interaction, and it's actually a very characteristic interaction with a plateau here, and then like a decay, and the decay is again 1 over r to the 6. But it's at a much smaller energy scale. But of course, that said, we've also bought a lot of lifetime that you can that you don't have to worry about, because you're basically still in the ground state. You only get a little bit of decay because you admix the Rydberg state. So that's kind of the transition going from bare Rydberg excitations to Rydberg. And saying that, a Rydberg gas interaction is essentially an interaction modified light shift. So that's a very intuitive way of seeing it. So just to summarize this a little bit, so what have we accomplished by detuning from resonance? Well, we've accomplished getting longer lifetimes, so we extended the lifetime because we only spent a small amount of our time essentially in the Rydberg state, if you like, only admixed the Rydberg state. That will hopefully allow us at one point to go to motional timescales. But we've also just gotten a switchable and tunable long-range interaction that has this scaling strength. And switchable and tunable is actually something you don't really have just by resonance deciding. And switchable tunable comes back to the fact that we're using the light to address these atoms. So we can now actually switch on and off these interactions at will, and we can build spin models similar to the ones I've shown you, where you just switch on or modulate or vary strength of interactions. Whereas in the case before, it was either all or nothing. So either you were in the Rydberg state and had full interaction, or you were in the ground state and had no interaction. So this is kind of a new thing that addressed like light-induced interactions give you over the bare interactions. And this is actually also what I'm going to focus on in the next couple of slides, because we of course have to verify first that this concept works, and we do that in this spin model. And just to make this clear, so before we were actually encoding the spin model in the ground and Rydberg state, so spin down to the ground, spin up to the Rydberg state, it would be exciting more or less close to resonance. Whereas in this case, we will actually talk about spin models where both spins are encoded in the ground state. So that's a conceptual difference over Rydberg dressing compared to the direct excitation. And of course, I already said that, so everything I said so far was kind of a theoretical concept. So there are different proposals about this admixing the interactions of two Rydberg states to the ground state, but it's not been shown, or it hasn't been shown. And the first thing we wanted was actually to show that what was predicted is true, and we wanted to do that in a spin language. So what we set out doing was actually to try seeing the interaction in a quench experiment. And in order to do that, we paired transfers a spin in a spin chain, in a state aligned with the y-axis on the block sphere. So we started with all spins 1c and applied the pi over 2 microwave pulse such that all point in the y direction. And then we quench on a spin-spin interaction with this rest interaction now. So it's this kind of characteristic soft core interaction with a CZ character. And of course, because the y spin eigenstates are not eigenstates of C, you would expect some dynamics. And the dynamics you expect is this revival dynamics. You start with a fully polarized chain, and then interactions kind of dephase you, and then because of finite number of frequencies in the system, we would actually expect these revivals, and these revivals would kind of carry the trait of this interaction. This is actually a very good way to learn about the shape of the interaction. And we do this experiment, and in order to see what's going on, you can actually just take a snapshot of the atom after the experiment. So here you see the initially prepared chain, so this is a 1D experiment again, with 10 spins along a line, and then as time evolves, you see like some spins make it to the left, some spins make it to the right, and left and right in this case means spin left and spin right actually. And you can actually see that the numbers in spin left and spin right vary over time. That's exactly how we would get this spin magnetization, how we would extract it. And that's what's actually shown here. So just taking these pictures and evaluating a magnetization, you see what you expect. You start with a fully magnetized chain, and then we demagnetize due to interaction. You see these revival, like these speedings coming up, and it's characteristic for the interaction scale, like for the stress interaction, where these speedings show up. And everything here is actually in quite good agreement with what we expect from theory. So there's basically no parameter in the theory. It's just like the theory curve that we would expect for our system to be valid. And we see a very nice agreement, which tells us that, okay, yes, it seems like the stress interactions actually are there, and they act the way we think they do. And just to give you some idea, interaction strengths that we can realize here are much smaller than what we get with their Rydberg interactions. So we've gone down from gigahertz to kilohertz, like 10 kilohertz, but we've also pushed the coherence time into the millisecond regime. And millisecond is kind of where you would say, okay, this is now comparable to tunneling in optical lattices, so it looks like we've bridged a large bit of gap from high energy, let's say Rydberg physics, to this low energy optical lattices. You're not all the way there, but I think it's pretty hopeful that we can make it. Good. So this was 1D. The question is, does it also work in 2D? And this is a very long story. I'm going to try to make it short. So in 2D, we can do a similar experiment. We can actually start from a 2D spin lattice, and we can see the effect of the interaction as a spin-spin correlation going up in a interferometric measurement. I don't want to go into details. If you want, you can ask me later about it. So you can actually see the salient features of this interaction. It's kind of an interaction that acts over more than the nearest neighbor, and it's an interaction that we can also tune very easily. So in this case, the interaction was chosen, the quantization axis using magnetic field was chosen for the interaction to be symmetric, and changing the magnetic field direction from out of plane to in the plane, we can actually tune it from isotropic to anisotropic. But there's a problem in 2D, and the problem is we have much stronger dissipation than what we think. The timescale associated with the inverse interaction is like 500 microseconds, whereas the coherence time we see only 130 microseconds. We think there is some Rydberg physics that's not well understood yet that smooths out those coherence times. So this is a big open question. I think 1D seems to work quite well, but 2D I think there's still some open issues there. And one thing that is very important with these 2D problems is to understand all the dissipation channels associated with the Rydberg atoms, the Rydberg states themselves. And one channel that we didn't think of first is what I'm going to show you in the next slide. It's actually a channel where you can form molecules between two Rydberg atoms. And those are the so-called Rydberg macrodimers, and what they are will come up in the next slide. So this is a very important lesson that we learned, that there are effects in these Rydberg, with these many Rydberg atoms, that you have to take into account to actually get rid of all the dissipation channels you don't want in your system. Okay, but so what are these Rydberg macrodimers? Let's step one step back. So this is again this interaction landscape for two atoms, two grounded atoms, one grounded, one Rydberg atom, and two Rydberg atoms. This is kind of the simple picture. So you can understand many things from this. But of course, real life is usually more complicated, and especially when you're up in the Rydberg manifold, you're close to ionization, and the levels get much more closely spaced. You have not only one Rydberg state, you have many, many Rydberg states close by. So it's actually very likely that sometimes you have other Rydberg states that, depending on how exactly the interactions work, could actually be attractively interacting here. And it's also not uncommon that in this attractive interaction, you actually, or with this attractive interaction curve, you actually get an avoided crossing due to a higher order. So it's possible that in these Rydberg manifolds, you don't just have like a 1 over R to the 6th dependence, like you would have it like out here or out here, but at sufficiently short distances, you also get like these spaghetti potentials, what they are called. So you can have like complex potentials, you can have bound states, and if these bound states or if these crossings happen sufficiently far out, which means that the distance here is sufficiently small, then you can actually have pure electrostatically bound molecules, which are coined or have been coined Rydberg macrodynamics. It's molecules consisting of 2 Rydberg atoms put together in such a binding potential. And what is special about them is actually that the binding lengths here of these electrostatically bound dimers can be in the micron regime. You can have really like micron size molecules, which is, just to make this clear, almost the size of a material. So it's a really huge molecule. And I already kind of told you the story, but I mean, the question is, can we see these? And can we see these realistically? And the answer is yes. Because in the state that we were looking at that time, we basically had exactly this configuration. So this is an actual potential calculation where we have like this state coming down here from a 35 to 1/2, 35 to 3/2 state, and we have a state shooting up that's a 1/2, 1/2 state, and they cross, but they actually don't cross, they avoid, and then you see these, you see this potential well. And we were actually like interested in the lower state here, and all of a sudden we would see effects that we didn't understand, and it turned out that it's due to this avoided crossing. So if you look at this potential minimum a bit more in detail, of course, we can also calculate eigenfunctions, and here's what they look like. They're very close to what you would expect in a harmonic oscillator. The potential is very harmonic actually in this approximation, and you can understand the properties actually very well. And one thing that is just kind of by accident, or happened by accident more or less here, is that if you look at this distance basically coincided in our lattice exactly with the diagonal of our lattice distance. So we were kind of lucky enough to hit exactly like to hit the right distance of the 2 atoms would exactly be at the right spacing to like associate them to a molecule. And this is actually what is shown here. So this is the relative pair wave function, this orange curve of 2 atoms, and it's kind of peaked more or less at the right point to associate these 2 atoms into these Rydberg molecules. So what do you see experimentally in this case? The experiment we did actually is just taking like a loss curve. So we just scan a laser starting far down here, all the way across these potential curves until we hit this avoided crossing. That's what you're going to see on the next slide. Maybe here, so we start far down with the detuning, and you see some coupling, some loss due to these 1 over R to the 6 curves, and you see the resonance where just lose all the atoms, and then the loss goes away. But then we see these series, these like very large series of bound states, molecular states, and zooming in, it's really a very, very regular series with some structure in the strand. And knowing the potentials, we can also, of course, calculate the line positions, and these are the lines, and they basically perfectly explain the positions of these minima. So this is the points where we associate 2 ground state atoms into 2 Rydberg atoms, and as a consequence, because they experience large forces, once they're in a Rydberg state, they actually get ejected from the lattice. So we see them as lost. And you can see really this nice agreement between an ab initio calculation of the Rydberg interaction potential and what we measure in the lab. And moreover, if you look at the signal shots here, this is a picture of a mod insulator, and we reconstruct it, so we check where an atom is and where there's no atom. You can actually see that we predominantly seem to be losing the atoms in pairs, which is exactly what you expect, because you're basically forming these molecules at a distance, again, of 700 nanometers. Okay, one more thing that you notice here is actually that looking at the orientation of these molecules, they seem to be predominantly aligned along this diagonal, right? And we were actually puzzled by this a lot, and we tried to think of reasons why this might be. And maybe for explaining why this is, a step I should follow. So yes, so you can actually, so why is this? You can actually intuitively guess that this might be the case, because depending on how you set your quantization axis, you either have the quantization axis orthogonal again to the 2D plane, in which case you expect like no specific angular orientation, or you can actually set your quantization axis in the plane, in which case it kind of makes sense that there's like a third direction of representation. So taking these density pictures, we can quantify what we see here using correlation, density-density correlation. So we basically ask how likely is it for three atoms to show up along one diagonal, or along the other diagonal, or in a symmetric way. And it turns out that what you expect, that if you have the quantization axis orthogonal to the plane of the atom, you kind of get this symmetric density-density correlation. So spins are equally, molecules are equally likely to form along one or the other diagonal. But if you put the polarization in the plane of the atoms, you see this stark anisotropy. But then one thing we got confused by is when we went from this mu equal 25 state to mu equal 26, because all of a sudden the orientation changed. And that's kind of then very weird, because we've just been talking now about like this quantization axis, which kind of would be associated with the light, like electronic coupling of the light. And then the question is, well, if you change the spatial wave function only, why should that change something? And that was actually very interesting to figure that out. We can understand this now fully. It's actually not just the electronic part of the wave function that controls the transition. It's also the Frank-Compton factor, so it's the motional part. And if you go from, let's say, mu equal 25 to mu equal 26, your motional state actually changes symmetry, is what you know from the harmonic oscillator. And it turns out that due to an interference effect between this electronic and the motional part of the wave function, you actually exactly start interfering destructively where we were interfering constructively before, and vice versa. You start to interfere constructively where we were interfering destructively before. And you can actually make like a table with these contributions. So the two-photon amplitude is like a sum of Frank-Compton factors and electronic factors. And it basically perfectly works out. So we exactly see the right behavior in terms of the signs of spatial and electronic factors to explain the tense, which was kind of nice to figure out. But to wrap this up, again, it's kind of something we more or less found by accident. It's an effect that you get when you detune from these Rydberg states, and it's a loss channel that you have to understand. And now knowing that it's actually a molecular series, we can also avoid it by just not tuning these radical states. That's a nice story that we more or less found by accident. Good. I think there's not too much time, but maybe very briefly, I'll very briefly touch upon the last thing, which is work that we've done recently in Berkeley. It's actually very different conceptually. It's work in progress, so it's kind of very preliminary, but I just want to present briefly the idea. So what I'm going to talk about now is has nothing to do with Rydberg atoms. It has nothing to do with optical lattices. It's just a gas of atoms, cold gas of atom in an optical cavity. And maybe just very crudely for me, for a beginner in cavity 3D, I think cavities are really great if you combine them with atoms, because you can actually use them for detection. Cavity light, the light leaking out of the cavity can be used to detect, again, cold atoms. You can actually introduce interactions using a cavity, because the photons in the cavity get kind of recycled by the cavity, and you can have like a single atom interacting with a photon that another atom has interacted before, which is effectively can effectively be seen as an interaction between two atoms. And you can use the cavity to prepare very interesting states. And this is of course something that Monica is an expert on, like all of these things. What we found interesting at Berkeley is actually whether it's possible to combine like this first point here, the detection aspect, with the preparation aspect. And we were kind of motivated a little bit by work from Aarhus, where people took a free-space gas, they detected it non-destructively using phase contrast imaging, and then depending on what they saw, they would actually feed back and prepare a certain number of atoms in a cloud. And we were actually asking ourselves, well, we have this cavity, which in principle should be able to do this better. And that's kind of what we were motivated by. So what I'm going to show you in the following is like how we combine the detection aspect of non-destructively probing a gas with a cavity with the preparation of a specific state of atoms, and actually with the preparation of an atomic state that has a reduced atom number. And just very briefly, what we're considering here is silver rubidium coupled to an optical cavity, but we're far detuned with the cavity resonance from atomic resonance. So there's an atom cavity detuning, and there's like a deep coherence in the free space, and there's a deep coherence, I want to say, into out of the cavity, so decay of photons out of the cavity. The dynamics of, or the physics of a gas coupled to of atoms coupled to a cavity is conventionally described by this Cummings homotony, which is basically many atoms coupling to a single cavity mode. And in the limit where this density A is large, you can actually basically eliminate the excited state of this two-level system, and you're left with basically a very simple Hamiltonian that is like a frequency, and then an atom number tuning added onto this frequency. So that's the main idea basically of our scheme. We want to basically measure this atom number dependent shift of the cavity resonance in order to then use that non-destructively, in order to use that information and then prepare a certain atom. And the way this works is basically to kind of have this shifted due to this n times t squared over that. Okay, to have to use this shifted cavity resonance, then place a beam here to measure at what time, depending on the atom number, this beam actually starts getting resonant with the cavity, and at which point we will actually see light getting through the cavity. And this is exactly what we do, and the way we measure this is actually using a heterodyne detector. And what we see in a conventional system, in a typical experiment, when the peak actually starts moving through our probe beam, is we see enhanced transmission once the beam gets resonant with the cavity. So we actually have a signal here that tells us, depending on some time where we spill atoms, well, how many atoms are there, and basically inverting our known behavior for the detuning versus atom number. And then we can actually go and set some trigger level and feed that that point when the cavity transmission hits that trigger, feed that back to our system, and then stop kind of that atom loss. And the way we do that is actually do an evaporation, a hybrid optical and magnetic trap, where we apply a strong magnetic field gradient to spill atoms out of that trap, and once the trigger level is hit, we just like make the trap deep, and we stop that atom loss. And that's kind of a fast feedback, because we can stop the atom loss almost immediately, so we can actually continuously monitor this, and as soon as we hit the trigger, we just stop it. Okay, that's conceptually very simple. The question is, does it work in an experiment? And here's kind of a typical atom number distribution, very few shots. And actually you can see where you see like how the atom numbers are distributed in our experiment. You can see the experiment is not super stable. We have a super broad atom number distribution. This was maybe a particularly bad day. And then we do this feedback, and we can actually check in the same sequence of experiments, because it's non-destructively, whether our feedback works. So we do the feedback, we measure the atom number, we do the feedback, and then we measure the atom number before. So this is the initial atom number, and this is kind of the final atom number after the feedback. You can see like it basically collapses very well to a single peak. And how does this look like as a trace? You see these very large fluctuations for different shots before doing the feedback and after the feedback. Straight and nice. Of course, the question is now, how well does it work, and what's the physics that limits it, or how well can we do, basically. And this is like very preliminary, so we've only taken very few data points here, but you can actually see that, first of all, we can push this width of this final atom number distribution below what you would expect from Poissonian statistics, so below like Poissonian atom number fluctuations, which is nice, because that's kind of a thing that you would not get without like special interaction effects, for example. And there's also kind of an interesting trend which we started exploring versus atom cavity detuning, which is basically the factor of how strongly you couple your atoms to the cavity. And we see kind of there's an interesting minimum, and I've put some theory pairs, some calculations below that. And we can reproduce what we see, and actually the limiting factors here seems like are technical. So this is like an uncertainty on our reader, on our cavity, that limits us on this large detunings, because the ships get smaller and smaller. So we have to know our cavity detuning better and better, and we're actually technically limited at that point. And then for short, for stronger couplings, more resonant light, let's say, we're actually starting to get limited by scattering. At least that's what we think. And actually, there's one thing that is missing from the plot. So you see here, there's kind of the discrepancy. We actually think that there's also cavity optical mechanics starting to limit these small detunings. But that's stuff that we're going to explore. But just to briefly summarize, it's actually already nice. You can see that we can consistently prepare atom numbers below shot lines. And the question is, of course, can we do this? Can we push this and see single atom sensitive errors? So can we actually take a cloud of 2,000 atoms and say in the end we want a 501 atom model? So this is kind of an open question at this point. The detection side should work in principle. That's actually been shown. The question is, does the feedback and everything work sufficiently well? And with this, I'd like to wrap up and finish. So I've shown you kind of the stuff we did in Munich on these long-range interacting gases, Rydberg interactions, which you can use to explore easing physics and try to, also combine it with motion in lattices, trying to bridge these energy gaps that are there using Rydberg dressing. We found these funny Rydberg macrodynamics that we were so excited about. And like more recently, the atom number stabilization project is kind of open-ended project, and we hope that we can actually push this project. And with that, I'd like to thank the team, obviously. So there's a big group in Munich that I had the pleasure to work with, especially Christian, the sub-PI, and Emmanuel, the PI, and of course also the great team at Berkeley that we work together with to get these kind of results. And thank you for your
So thanks for a wonderful talk. Time for a few questions.
So what happens to the macro timers once they're formed?
Yeah, that's a good question. So we think actually, so one of the Rydberg atoms will decay after 20 microseconds.
Okay.
And then
So on that same subject, you showed spectra with positive detuning and negative detuning, and that was from the resonance line
yes.
of the Rydberg?
Yes, right.
So two lines on the...
Very good. Yeah, that puzzled us for a long time, but we figured it out. It's so you're talking about these two lines.
Yeah.
They actually also show up somewhere here. It's the peak frequency between our lattice beams. And we think it's actually some kind of, it must be some Raman assisted excitation of these macrodimers that somehow excited from one lattice beam into, like, I think it's a Raman process from lattice beam to lattice beam via the Rydberg beam. So it's exactly the beating frequency between our two lattices. So it's a little bit wishy-washy, but I think that's it's exactly the frequency. We are sure that that's not physics. So we were thinking that this would be physics too, but at one point we figured out it's not. Or other physics, not Rydberg physics.
So there are some ideas for using these molecular states to enhance the dress interactions. Is it something that you looked at all, or?
Yeah, so that was the initial idea of looking at these. So it turns out that if you dress like close to these, there's proposals that if you dress close to these maxima, you can actually enhance your interaction strength over the coherence. In principle, because you basically gain pair state admixture without actually, you can enhance your pair state admixture without getting more single atom admixture. That's the basic idea. And it turns out that dressing to these macro diameters actually is exactly the same. You can just dress to the molecular state, you will get exactly the same enhancement. But something that people didn't take into account when thinking about this is what you get in these macro diameters is the spatial overlap. So your dressing strength very strongly depends on the coupling strength. And of course, you're always going to be like limited in coupling strength because you have that confounding factor that cuts down your coupling strength. And I think this is what you get in dressing to these molecular states. And I think you also get it actually when you dress to maximum here, because it's you're just like it depends on how flat your maximum will be, and that's just like a scale down your interaction strength. So yeah, you can find very flat potentials where the ratio is a bit better, but I think it's going to be hard.
Because you also might get some very strange shape of the interaction.
Yes.
Potential.
Yeah.
Okay.
So
Yeah.
if you take the macro diamond here, you can actually like make an interaction that is exactly effective at √2 times your lattice spacing. So it's exactly like basically to within whatever the extent of this wave packet is. So that's also very interesting.
Any last questions for Johannes? Guys, let's thank him one more time.